Have you ever felt like data center networking is just this, I don't know, this incredibly complicated beast?
Yeah, it can definitely feel like that sometimes.
Today, we're going to dive deep into Cisco's application-centric infrastructure.
ACI.
ACI, that's right.
Oh, yeah.
And we've got a whole bunch of information that you've shared with us.
Yeah.
Everything from, kind of like high-level overviews to like the really, really nitty-gritty technical details.
Mm-hmm.
Our goal here is to pull out, like, what are the essential insights? What do you really need to know about ACI?
Right.
Without having to read through, like, pages and pages of documentation.
Yeah, like a cheat sheet almost.
Exactly. We're going to explore the core components of Cisco ACI,
Hmm.
how they all work together, and, what are the benefits of using this approach.
Especially in today's data centers, right?
Definitely today's data centers. We'll touch on everything. From the physical layout,
Hmm.
like the actual hardware,
The boxes themselves.
to the software brains behind it all.
The magic, the secret sauce.
Okay, so the first thing that kind of pops out when you start looking into ACI is this thing called the ACI fabric.
Right.
And it seems to be built entirely on these Cisco Nexus 9000 series spine and leaf switches.
Yeah, you'll see that mentioned a lot, that spine leaf topology. It's kind of like their key thing.
Yeah, and it's mentioned repeatedly, this spine leaf topology.
Mm-hmm.
So what is it about this particular way of connecting switches?
Well, it's really the foundation of how ACI performs and scales.
Mm.
It's all about how these switches are interconnected very deliberately. So all your endpoints, your servers, your storage, even those APEC controllers we'll talk about later,
Right.
they connect exclusively to the leaf switches,
Only the leaves.
only the leaves, and then the leaf switches only connect to the spines.
Okay.
So no direct leaf-to-leaf connections, and spines don't connect to each other directly either.
It's very, like, structured.
It is. And you'll always have at least two spines. Redundancy, right? That's really important.
Makes sense. So everything has its place.
Ex-
You mentioned APIC, the Application Policy Infrastructure Controller.
Yeah.
That sounds important.
It is.
That sounds like the brains of the operation.
It's like the central intelligence, the policy engine.
Yeah.
You define what you want your network to do, and the AP makes it happen across the fabric. It's the management plane where you do all your configuration and monitoring.
Okay, so it's where you tell the network what to do.
Exactly. But here's the thing. It doesn't actually sit in the path of your network traffic.
Oh, interesting.
It's not like a router or a firewall, and it doesn't handle those low-level control plane functions directly.
So it's like the architect, right? Designs the building, but doesn't actually lay every brick.
Perfect analogy.
So I'm seeing here that, we're talking about a redundant cluster of at least 3 APIC servers.
Right, and often they run on those Cisco UCS C-series appliances.
Why is this redundancy so important?
Well, think about it. What if one of those APIC servers goes down? You don't want your whole network management to grind to a halt. The other two APICs can keep things running smoothly, no interruption. They'll keep managing the fabric, enforcing those policies you've set up.
So it's like having a backup, but like 2 backups.
Exactly. Having at least 3 means there's always a majority, a quorum. No single point of failure can take down the whole management system. And this is also what allows the APIC to do automated provisioning and management, really take care of things for you.
That's pretty slick. Now, there was also a brief mention of NDFC.
Cisco Nexus Dashboard Fabric Controller.
That's a mouthful. How does that fit into the whole ECI world?
So NDFC is another management option that Cisco offers,
Okay,
and you access it through the Cisco Nexus dashboard.
got it.
Think of it this way. The APIC is really focused on a single ACI fabric.
Okay.
But Nexus Dashboard, that gives you a more unified experience, especially if you're working with multiple ACI fabrics.
Or even a mix of, ACI and maybe some older traditional networks.
Exactly. It's about having that broader perspective, centralized control across different environments.
So APIC is for a single ACI fabric. Nexus Dashboard is like the bigger picture.
You got it.
Okay. Let's circle back to the spine leaf topology for a second.
Sure.
It seems like it's more than just a way to connect switches.
Oh, absolutely.
There's some real advantages to using this structure.
A whole bunch of them, actually. For starters, it's simple. Since every leaf connects to every spine and there are no other direct connections,
Right.
it makes it so much easier to build, test, and maintain the network. And it scales beautifully. Need more ports for your servers, just add more leaves. Need more bandwidth, add more spines.
So it's flexible. You can grow it as you need.
Exactly.
Yeah.
And because it's symmetrical, every connection between endpoints,
Any 2 endpoints.
any 2 endpoints in the fabric will always go through the same number of hops, usually just 2.
Yeah.
From the source leaf up to a spine, down to the destination leaf.
2 hops every time.
Every time. This means consistent latency. And that's super important for applications that are, sensitive to delays, not like those older hierarchical models where the number of hops could vary wildly.
Right, right. So it's predictable. You know what to expect.
Exactly.
Okay. And I've got it right here. I'm looking at the advantages. It says simple, consistent, scalable, symmetrical for optimization, cost-effective for high bandwidth, low latency, and oversubscription.
It's quite a list. Gets rid of a lot of those headaches from the old designs.
So we've talked about the hardware, the physical part of the ACI fabric.
The foundation.
But how does it actually get up and running?
Well, you got to start with the APIC, right?
Right.
And there's an initial setup process, got to configure those crucial parameters.
So what are we talking about here? Like, what are the things you absolutely need to set up right from the start?
Well, first things first, you power up your API, and you'll go through this console setup.
Okay.
You'll give your fabric a name. That's its unique ID.
The name of the whole thing. Got it.
Then you tell it how many controllers are in your cluster. 3 is the usual number for that redundancy we talked about. And you give each APIC its own ID and a name, so you can tell them apart.
Fabric name, number of controllers, and then each controller gets its own ID and a name. Okay, what else is super important at this early stage?
The TEP address pool. TEP stands for tunnel endpoint, and these IP addresses are used internally for that VXLAN overlay network ACI uses.
VXLAN. We'll get to that later.
Right, but for now, just know that you got to set up this pool of addresses. The default is 10.0.0.016.
Okay.
But, big but, it can't overlap with any other subnets on your network. And for a 3 APIC cluster, you need at least a 23 subnet. You also need to set a VLAN ID for the infrastructure network. VLAN 3967 is what Cisco recommends.
Okay.
Again, super important. This VLAN needs to be just for ACI, can't be used anywhere else.
So dedicated IP and VLAN ranges just for ACI, keep it separate.
Exactly. Keeps things clean and prevents conflicts.
And how do you actually get into the APIC to manage it?
You'll set up the out-of-band management IP address. That's the main IP you use to access the APIC through the UI, the CLI, or even through its APIs.
So that's how you talk to it. Got it.
Right. And you set the default gateway for that out-of-band management network as well. Oh, and of course you set up the admin password. Got to keep things secure, right?
Yeah.
Make sure it's a strong one.
At least 8 characters, 1 special character, all that good stuff.
Yep. And one last thing, this is really important. The clocks on the APIC and the switches, they need to be synchronized.
Like perfectly in sync.
As much as possible, yeah. Otherwise, that whole fabric discovery process can have problems.
So to recap, we've got the fabric name, the controller setup, the IP addresses and VLANs, the management access, a strong password, and make sure all the clocks are synced up.
You got it. That's the foundation.
Okay, so APIC's up and running, got the basic configuration done. How does it find all the switches in the fabric? How does it bring them into the fold?
That's the beauty of it. It's all automated. Well, mostly. So the first step is the APIC needs to discover those leaf switches that are physically connected to it.
The one's plugged right in.
Right. And it does that using LLDP, the link layer discovery protocol.
LLDP.
So the APIC finds those leaves, and then each leaf switch sends out a DHCP request. DHCP, Dynamic Host Configuration Protocol.
You have to get an IP address.
Exactly.
Yeah.
And the APIC responds, it gives the leaf a TEP IP address from that pool you set up earlier.
So LODP for the initial hello, and then DHCP to get an IP address on the internal network. What happens next?
So within that DHCP offer packet, the APIC also sends the switch some vital information.
Like what?
It tells the switch where to get its boot file. That's the operating system, the firmware, the brains of the switch.
Oh, right. So it's telling it, hey, go download your brain from over here.
Exactly. The switch then grabs that boot file from the APIC. It uses HTTP GET on port 7777.
Okay, so it's downloading the software.
Right. And once it's got that, it starts listening on a specific port 12183. That's when the AP initiates an encrypted TCP session with the switch.
Encrypted. Why encrypted?
Well, you're sending sensitive information. Right. Configuration details, policies, all that stuff. You don't want that floating around in the open.
Makes sense.
So this encrypted connection, it's called IFM, Policy Element Intra-Fabric Messaging. That's how they talk to each other securely.
IFM. Got it. It's their secure channel.
Exactly. And it uses SSL encryption with embedded 1024-bit SSL keys. Very secure.
Sounds pretty robust.
Yeah.
So what about all the other switches in the fabric? The ones that aren't directly connected to the APA?
It's a chain reaction.
Oh, interesting.
Starts with those directly connected leaf switches.
Right, the ones we just talked about.
They've got their TP addresses, their boot files, they're up and running. Now, they use LLDP to discover the spine switches they're connected to. And then the same process repeats. DHCP request, TP address allocation, boot file download, IFM setup. Each node discovers its neighbors, gets its configuration, and joins the fabric.
It just expands outwards from the APIC?
Exactly, like a ripple
Yeah.
effect. And something the sources pointed out, LLDP neighbor discovery and the control plane ISIS protocol, they converge while all this bootstrapping is going on.
ISIS, that's another one of those networking protocols.
It is, but don't worry about the specifics for now. The point is, it's all happening in parallel, getting the fabric up and running.
So everything is finding its place, getting configured all automatically.
Pretty cool, huh?
What about the APICs themselves? How do they discover each other, form that cluster?
They talk to each other through the switches. They use internal IP addresses for communication within ACI, and you guessed it, they use LLDP to discover those IP addresses.
LLDP again.
It's a busy protocol. So they find each other, validate each other, and then update their local appliance vector. It's basically a list of each APIC's ID, its IP address, and a unique identifier, a UUID.
Okay, so they're all sharing information, making sure they have the same picture of who's who in the cluster.
Precisely. And they program the leaf switches with this updated information, which then gets spread to all the other switches.
So it's a constant exchange of information to keep everything consistent.
Exactly.
Now, one thing I noticed in the materials is that while the AP auto-discovers the switches, there's still a manual step to actually add them as Fabric node members. Why is that?
It's a security measure, a way to control what actually becomes part of your managed fabric.
So even though the AP sees the switch,
It won't just automatically let it in. You have to go into the APIC's GUI, the graphical user interface, and specifically add it as a Fabric node member. You put in the node ID, the serial number, give it a name. It's a way to make sure that only authorized switches are allowed in.
kind of like a security checkpoint.
Exactly.
Okay. I'm also seeing here that for node IDs, they recommend using numbers greater than 101.
Right, because IDs 1 to 100 are reserved for the Apex nodes themselves.
Oh, that makes sense. And they say to use continuous ranges for leaf and spine nodes.
Keeps things organized, easier to manage.
Okay, so the APIC discovers the hardware, but you, the administrator, decide what actually gets incorporated into the ACI environment.
You're in control.
All right. Now let's shift gears and talk about how traffic actually moves within the ACI fabric.
Okay.
This VXLAN tagging keeps popping up.
It's a big deal in ACI.
What is it and why is it so important?
All right, so VXLAN stands for Virtual Extensible LAN.
Gotcha.
In ACI, every single packet of data gets encapsulated with this special Cisco ACI VXLAN header.
It's like putting it in an envelope.
Kind of, but this envelope has instructions on it.
Instructions.
Yeah, it tells the network how to handle the packet. It carries information about the policy, the security rules, all sorts of things.
Oh, so it's not just about getting it from point A to point B.
Nope, it's about making sure it gets there securely and according to the rules you've set up.
So VXLAN is like the delivery truck with a super detailed map and instructions.
That's a great way to think about it. Now, VXLAN itself is what we call a Layer 2 overlay network. It runs on top of a regular Layer 3 IP network.
Layers, networking is all about layers.
It is. But the cool thing about VXLAN is that it lets you create way more network segments than you could with traditional VLANs.
How many more are we talking?
With VLANs, you're limited to about 4,000. VXLAN, 16 million.
Wow, that's a huge difference.
It is, and each segment gets its own unique identifier, a VXLAN network identifier, or VNID. This VNID tells the ACI fabric which forwarding group the packet belongs to.
So lots of segments, each with its own ID. Makes sense.
And this is super helpful in data centers where you've got, lots of different tenants or applications all needing their own little slice of the network.
Right, like separate apartments in a building.
Exactly. And it's also great for something called microsegmentation, where you can apply really granular security policies.
So you mentioned this Cisco ACI VXLAN header.
Mm-hmm.
It's got some specific fields in it, right?
It does. There's the G bit, the D bit, the A bit, and the group policy ID.
Okay, lots of bits. What do they all mean?
Well, the G bit stands for group-based policy extension. It basically tells the network if that extension is being used. If it's set to 1, it means the packet's source group membership is included in the group policy ID.
Okay, so it's like a flag saying, hey, Pay attention to the group policy here.
Exactly. Then you've got the D bit, the don't learn bit. When it's set, it tells the network device that receives the packet not to learn the source MS address.
Interesting. So it's saying, don't remember where this came from.
Right. Then there's the A bit, policy applied bit. If it's set to 1, it means the right policy has already been applied to the packet, so no need to do it again.
Like a stamp of approval. Already checked, good to go.
Exactly. If it's 0, it means the policy still needs to be enforced. And finally, you have the group policy ID. It's a 16-bit number that identifies the source group.
So these bits and the group policy ID, they're basically carrying all this extra policy information with the traffic, making sure the network knows how to handle it.
It's all about enforcing those policies consistently.
Got it. So now we get to VTEPs, VXLAN tunnel endpoints.
Those are the guys that do the heavy lifting.
What do they actually do?
They're the ones that map those tenant end devices, like your servers, to the right VXLAN segments, and they handle the encapsulation and de-encapsulation of the traffic.
So they're like translators, taking the traffic from the regular network and putting it into those VXLAN tunnels.
Perfect analogy. Each VTEP has 2 main types of interfaces. One connected to the local area network, the LAN for local bridging, and another one connected to the transport network. That's the underlying IP network that carries the VXLAN tunnels.
Right, the highway for those VXLAN trucks. And each VTEP gets its own IP address, right?
It does. That's how it's identified on the transport network.
So different VTEPs might do different things depending on the type of traffic.
Exactly. For known unicast traffic, where we already know the destination MS address, the traffic goes directly from one leaf VTT IP to another.
Straight shot.
For unknown unicast traffic, where we don't know the destination MS address yet, it goes to an Anycast spine proxy VTT.
Pine proxy, what's that?
It's a VTT on a spine switch that helps locate the destination endpoint within the fabric.
Okay, so it's like a directory assistance for the network.
Pretty much.
Yeah.
And then you have multicast and broadcast traffic that gets sent to a group VTT on any leaf switch that has members of that multicast group.
So different types of traffic, different VTP behaviors.
Right. Oh, and one more thing. VTTPs don't have to be on physical switches. They can also be on virtual switches.
Like in a virtualized environment.
Exactly, like on a Cisco AVE, the Application Virtual Edge. That lets you extend ACI policies into your virtual world.
Very cool. So we've got the traffic encapsulated, we've got the VTPs managing it, moving it around. How does ACI actually decide where to send each packet?
It can handle both layer 2 and layer 3 forwarding. And the best part is you don't have to change anything on your applications.
That's good. Less work for us.
Every leaf switch has this thing called an SVI, a switch virtual interface.
Okay.
It acts like a distributed default gateway. So from an endpoint's point of view, its gateway is always local on the leaf switch it's connected to.
Makes sense.
Now, the fabric learns MAC and IP addresses through something called conversational learning.
Conversational.
It learns as devices communicate. This information is stored in a cache on each leaf switch.
Okay, so each leaf has its own little address book.
Right, but the master address book, the authoritative source for all endpoint MAC and IP addresses, that's the QFB database, the Council of Oracle Protocol database, and that's on the spine switches.
So leaves have a local copy, spines have the master copy.
You got it.
Now, what happens if a leaf switch needs to forward traffic to a remote endpoint, one that's not in its local cache?
That's where those spine proxies come in. If a leaf doesn't know where to send a packet, it sends it up to a spine switch. Okay. The spine has the COAT database, so it knows where every endpoint is. It then forwards the packet to the correct destination leaf switch.
Ah, so the spine acts like a traffic cop.
Exactly. But over time, the leaves learn about remote endpoints directly from other leaves. This is called remote endpoint learning. So eventually, most traffic can go straight from source leaf to destination leaf without bothering the spine.
So it gets smarter as it goes along.
Exactly. More efficient.
Now, what about traffic that doesn't use IP addresses? How does ACI handle that?
It learns MAC addresses, just like it learns IP addresses.
Okay.
And then it looks at the destination MAC address. If it's the MAC address of the local router interface, the SVI, it routes the packet. Otherwise, if it's a different MA address within the same bridge domain, it bridges the packet.
So it figures out whether to route or bridge based on the MC address.
Exactly.
Yeah.
Just like traditional networking, but all happening within this ACI fabric.
Got it.
Hmm.
Now, let's talk a little bit more about the Cisco Nexus dashboard.
Sure.
The sources talk about it being a single point of management. Why is that so important for ACI?
Well, you can imagine managing a big data center network can get really complex.
Lots of moving parts.
Lots of them. Nexus Dashboard is designed to simplify that. It's your one-stop shop for monitoring and managing everything. Your ACI fabrics, your traditional NXOS networks, even your cloud environments.
So you don't have to jump between different tools and interfaces.
Exactly. You get this unified view of your entire infrastructure. You can see the health, the performance, the security posture, all in one place.
Sounds much easier than juggling a bunch of different tools. What are some of the other benefits that Nexus Dashboard brings to ACI management?
Well, it's got a really intuitive graphical user interface. You can customize it to fit your role and the tasks you do. Plus, it's got single sign-on. So you log in once, and you can access all the different services and tools.
That's handy.
It also gives you really detailed health monitoring, and it makes deploying new services and applications much faster and easier. And as your infrastructure grows, Nexus Dashboard can scale right along with it. It can handle on-premises, data centers, multiple public clouds, edge computing, the whole shebang.
It's designed to handle that complexity.
Exactly. And it simplifies maintenance. You've got integrated lifecycle management. And it's also the central point for integrating third-party tools and automation.
So it's like the conductor of the orchestra, bringing everything together.
That's a great way to put it.
All right, so zooming out a bit, ACI is clearly Cisco's main SDN solution for data centers.
Software-defined networking, it's a big deal.
What does that mean in practice for ACI to be SDN?
SDN is all about separating the control plane from the data plane.
I remember those terms from earlier.
The control plane is the brains, the intelligence that decides where traffic goes. The data plane is the brawn, the hardware that actually moves the packets.
Okay.
In a traditional network, those two are tightly coupled. In SDN, they're separate.
What's the advantage of that?
It gives you centralized control. You can program the network as a whole instead of configuring each device individually.
So it's more flexible, more adaptable.
Much more. ACI specifically follows an intent-based, policy-driven model.
What does that mean?
You define what you want the network to do in terms of connectivity, security, performance, and the APIC translates that into specific configurations on the switches.
So you tell it what you want, and it figures out how to make it happen.
Exactly. It's much more agile and less error-prone than the old way of doing things.
So SDN is about that separation of control and data, and ACI implements that through this intent-based approach.
You got it.
And the materials list several advantages of ACI being an SDN solution. Can you summarize those for us?
Absolutely. First, you get resilience thanks to that spine leaf architecture and VXLAN. Then you get simplicity because the APIC is your single point of management.
Yep.
And then there's automation. You can use the APIC's REST APIs to do all sorts of cool things programmatically.
APIs, those are for developers, right?
Yeah, but they let you automate a lot of the network management tasks.
Got it.
And then there's security. ACI provides strong security both for traffic coming in and out of the data center and for traffic flowing between applications within the data center. It's all about centralizing those policies. And finally, you get flexibility. You can extend those same ACI policies to both physical and virtual devices, servers, virtual machines, containers, the whole lot.
So lots of benefits. Resilience, simplicity, automation, security, flexibility. It's quite a package.
It is. And it's worth noting that both the CLI and the GUI, those are just interfaces that interact with those underlying APIs.
So whether you like typing commands or clicking buttons, you're really using the same powerful backend.
Right. And ACI uses an object model for its API configuration, which makes automation even easier.
So the AP is the central controller, and you configure it through those northbound REST APIs, right?
Exactly.
The materials mentioned southbound APIs too. What's the difference?
So northbound APIs are for external communication. They let other systems like your orchestration tools or your cloud management platform talk to the APIC and control the ACI environment.
Okay.
Southbound APIs are for communication between the APIC and the network devices themselves.
So northbound is for talking to the outside world. Southbound is for talking to the switches.
You got it. And the sources made a good point about the history of SDN. OpenFlow was one of the first big SDN standards, but ACI uses a different protocol for its southbound communication, Offlex.
Offlex.
Which, by the way, has also been standardized by the IETF.
So lots of different pieces coming together to make this whole SDN thing work.
It's a whole ecosystem.
All right, let's dive into the concept of application-centric policies.
Okay.
That's like the heart of ACI, right?
It's right there in the name.
So what are the key concepts here?
The most important thing to understand is the concept of endpoint groups, or EPGs.
EPGs.
These are logical groupings of your endpoints, your servers, your virtual machines, based on the application they belong to or their function.
So instead of grouping things by their physical location or their IP address,
You group them by what they do.
so you might have a web server EPG or a database server EPG.
Exactly. It's a much more intuitive way to manage things.
And you can assign individual endpoints to these EPGs based on different criteria, right? Like their IP address, their MC address, even the port number they're using.
Absolutely. It's very flexible.
So EPGs are all about grouping things logically based on the application.
Right. And once you've defined your EPGs, you use contracts to control the traffic between them.
Contracts.
Yeah, they're like rules that say which EPGs can talk to each other and how.
So they're like access control lists, but for groups of devices.
Exactly. You can specify things like which protocols are allowed, which ports are open, all that good stuff.
And by default, any device within an EPG can talk to any other device in the same EPG.
That's right. But to communicate between different EPGs, you need a contract.
It's like having separate rooms in a house, and the contract is the door between them.
I like that analogy.
So what about bridge domains and application network profiles?
Okay, so a bridge domain is basically a layer 2 broadcast domain within ACI.
Okay.
It's where you configure your subnets, your VLANs, things like that. An application network profile, or ANP, is what ties everything together.
Yeah.
It maps your EPGs to one or more bridge domains.
So then ANP says, okay, this